Alright, here's another linear representation exercise, and this I'm actually recording from my new apartment, so we'll see how it goes. The rough thing is that it's summer and this place doesn't have central air conditioning. I have like window units, and so I had to turn the one off so that I could record without background noise, and this could be a little rough, but hopefully it doesn't get like boiling hot in here during the time when I'm filming this video. But I mean, I guess we'll see what happens. So anyways, so rho is the permutation representation. So X is a finite set on which G acts. So recall what does all this information tell us? That call rho is a map from G to G, the general linear group of some vector space V, where V has a basis of elements Vx, where X is an element of big X. And this basis is such that for all G and G, and for all X and X, rho G applied to Vx equals V of Gx. And this makes sense because G acts on X, and so Gx gives us another element of big X. Okay, so that's that. So let X equals n, the norm of X equals n, and x1 through xn be precisely the elements of big X. And let G be in big G, since Gx on X, G permutes the elements of X. It's just by definition. So define I, and this I isn't really necessary, but this is just going to be the set of indices from 1 to n. This is just to prevent me from having to write this 1 through n a bunch of times. So that's capital I, and we're going to let sigma g be an element of Sn, so permutation on n letters, such that for all I and j in capital I, which of course is the collection of indices, so these are I and j can each range from 1 to n, we're going to have sigma g of xi equals xj. No, this should be sigma g of I equals j, because this is Sn is the permutation of n letters, so we're only looking at the letters here. But sigma g of I equals j if and only if gxi equals xj. So this permutation is basically telling us how G is permuting the elements. So then rho G of Vxi is precisely Vxj, because rho G of Vxi will be V of Gxi, but Gxi we know is xj. Am I using sigma at all here? I guess this isn't. So you're right. I solved this problem quite a while ago, and I don't think I did the most straightforward thing. So here. I'm gonna redo this actually. I'm doing this on the fly, and that's dangerous. So call Kenny logins, blah blah blah. So for all G and G, for all Xi and X, there is some Xj and X such that rho G of Vxi equals Vxj. That's really all we need. The sigma thing helps you see like, oh, this is really just a permutation. But, I mean, we're dealing with groups here, so that's kind of obvious. All groups are subgroups of permutation groups, so you're always permuting things. So anyways, this means that rho G is precisely the so we want to write, is the matrix capital A equals Aij, where Aij is going to be 1 if rho G V xj equals xi. Why did I flip from xi to xj? Because that's how this is defined. 0 otherwise. Right? So, because what you have is you have this matrix A and you're multiplying on the left by some Vxi. And so what's going to happen? Well, let's say we've got a whole bunch of so here's it. I remember working through this and realizing that you had to flip these indices here, but I'm trying to see why it's obvious that that's what you have to do. Holy shit, it is getting really hot in here. Oh, I just swore I should link that out. Okay, so we are 8:10 into the movie. Alright, there is a little bit more to this problem than I initially thought. So what we're going to do now is assume, without loss of generality, that Vxi is EI. I think this is what I was assuming the whole time when I wrote this problem, but it doesn't necessarily need to be the case, but it kind of makes sense. You would think of it this way because you'd let EI just, you're sort of taking your vector space V of dimension n, and you're associating with each, you're associating the possible like entries in this vector space with the elements of capital X. And so like the first entry is going to correspond to x1 and the second entry to x2 and so on and so forth. And so what we're going to do is we're going to assume, I mean, we're not necessarily told that these basis vectors Vx have any particular dice form. All we know is that they're indexed by the elements x. But if we let Vxi equal EI, then things are a little simpler, and it just sort of makes sense, and it's easier to work with, and it's going to be easier in this next step. And so in particular, Vx rho g of EI is equal to EJ. For some j in for some j. Okay. So now what? So this then we can express we can express rho g as a matrix let's do it A sub g, which is just a matrix consisting of elements aij, where, what do we know about aij? We want it to be 1 if rho g of ej equals ei, and 0 otherwise. This flip of the indices is important because if you think about it, what do you want to happen? We want a blank equal blank, and if we look at a times ej, then we want this to, we want to look for which, let's say we have a times ej equals ei, then which entry in capital A do we want to be 1 to force this to happen? Well, ej is of course just 1 on the j entry, and because when we're doing matrix multiplication, we multiply each row at a time. What you want is for once you get down to the so you want this to be I. So once you get down to the ith row, you want there to be a 1 in the jth column. So that's where we want our 1 to be, and we want everything else to be 0. And that's precisely the ij entry of the matrix. And so that should show you why we flip the indices, why aij is 1 if rho g ej equals ei. Okay, so that's that. And so we can now compute the character chi of, okay, so I guess it's chi x of g, but like we're only dealing with, oh, and I guess this is S and G. Whatever. Chi x of S is equal to the trace of rho S, which is just the trace of this matrix AS, which is equal to, of course, what is the trace? It's just the sum from I equals 1 to n of AII equals sum of the indices I guess I should have used this. The indices I ranging from 1 to n such that AII equals 1, obviously. The order of this collection, because this sum will be precisely the number of indices such that AII is 1. Because AII is going to be either 1 or 0 because of how we've defined AG for G in our group G. Okay? So then what else? But we know AII. We know how to compute it. This is going to be all the I such that rho G of EI equals EI. But because we know how this linear representation acts on the basis elements, we know that this is precisely the I such that, I'm using G again, should be S. I need to use the next line as well. So this is just the indices I, or the number of indices I, such that S of EI equals EI. But that's precisely, let's see here, this is x to the s, which is just the notation for the number of elements of x which are fixed by s. Because for each of these indices, I, we have EI equals, this is SEI equals EI. But then we could just remember, because EI equals XI, or VXI, and this is just VX, the number of elements of X fixed by S. I such that SXI equals XI. Does this make sense? Because S doesn't really act. No, it does act on S. The basis. Maybe this is a little more confusing. Okay, so S doesn't. Right, yeah, okay, so rho S of EI equals EI. Oh, so rho S VXI equals VXJ. Okay, so let's actually go back a little bit. I'm sorry, this is why I should have made a new script before making this video, but oh well, we're already here, so we might as well just keep going. Again, I'm not so. I guess I should be a little more concerned about the quality of my videos, but I'm very much concerned about the quantity of videos. And I want that to be as large as possible, even if I sacrifice having a little, like, few mistakes and mess ups in some of the exercises. But anyways, what was I doing? Rho SEI. So yeah, this is rho S of VXI equals VXI. And so now this is the number of elements I such that S applied to XI equals XI. Right, because that's how the basis. Well, right. Oh, yeah, of course. Because what's really going on here is What's really going on here is that this is v. We want the ones where vxi is equal to rho sub s of vxi. But we know what the formula for this is. This is precisely v sub sxi. Okay, so that's what we really need, is that we need the I such that v sub xi is equal to v sub sxi, because that happens precisely when xi equals sxi. And then this is precisely the order of the set of elements which are the set of elements in X which are fixed by this element S. Okay, so sorry about all the confusion that happened in this problem. But yeah, there we go. That's how we do this problem, and this completes our proof.